Hello, I'll be your instructor for this course on using SQL to turn raw data into actionable insights. We'll build on our foundational knowledge of SQL, learn how to reveal insights, and how to present our results clearly. While SQL can be used to create and modify databases, the focus of this course will be querying databases. Recall that a query is a request for data from a database. In this course, we'll look at how to execute a query for a database using keywords that will enable us to count and view all or a specified amount of records. We'll go over common SQL errors, style guidelines, and the order in which our code will execute. We'll cover how to filter data using various techniques, how to use aggregate functions, and finally, how to sort and group the results. We'll be using PostgreSQL throughout. We will work with a films database containing 4 tables: films, reviews, people, and roles. Our database schema, pictured here, shows the table names, field names, and data types. Here we go with our first new keyword. Let's say we wanted to count something from our people table. The count function lets us do this by returning the number of records with a value in a field. For example, to count the number of birth dates present in the people table, we will use select count birth date from people. The result is 6,152 birth dates. We've used the alias count birth dates for the field name in this example to make the results more readable. If we want to count more than one field, we need to use count multiple times. Here we are counting both the number of names and birth dates present in the people table. Using count with a field name tells us how many values are in a field. However, if we want to count the number of records in a table, we can call count with an asterisk. For example, this code gives the total number of records in the people table. The asterisk represents all fields. Passing the asterisk to count is a shortcut for counting the total number of records. Often, our results will include duplicates. We can use the distinct keyword to select all the unique values from a field. This might be useful if, for example, we're interested in knowing which languages are represented in the films table. Adding distinct to our query will remove all duplicates, as we can see here. Combining count with distinct is also common to count the number of unique values in a field. This query counts the number of distinct birth dates in the people table. Let's take a moment to consider why this number is different from the birth date count of 6,152 we got before. Some people in our table likely share the same birthday. Count would include all the duplicates while distinct counts all of the unique dates, no matter how many times they come up. Fantastic work on using count and distinct. Now that we've flexed our SQL muscle a bit, we'll take a small step back and better understand how SQL code works. Unlike many programming languages, SQL code is not processed in the order it is written. Consider we want to grab a coat from a closet. First, we need to know which closet contains the coats. This is similar to the from statement, which is the first line to be processed. Before any data can be selected, the table from which the data will be selected needs to be indicated. Next, our selection is made. Finally, the results are refined. Here we use the limit keyword that limits the results to a specified number of records. In this case, we only want to return the first 10 names from the people table. Knowing processing order is especially useful when debugging and aliasing fields and tables. Suppose we need to refer to an alias later on in our code. In that case, that alias will only make sense to a processor when its declaration in the select statement is processed before the alias reference is made elsewhere in the query. Before we begin working with more advanced queries, it's useful to know more about debugging SQL code and how to read the error messages. Some messages are extremely helpful, pinpointing and even suggesting a solution for the error, as this message does when we misspell the name field we'd like to select. Other common errors may involve incorrect capitalization or punctuation. Other error messages are less helpful and require us to review our code more closely. Forgetting a comma is a very common error. Let's say we've drafted this code to find all titles, country of origin, and duration of films. The error message will alert us to the general location of the error using a caret below the line of code. which in this case points to the country field name. We must examine the code a little further, though, to discover the missing comma is between country and duration. SQL displays a similar error message when a keyword is misspelled, but this time, the caret indicator below the offending line is spot on. There are a few more SQL errors out there, but the three mentioned in this lesson will be the most common ones we will encounter. Debugging is a major skill, and the best way to master this skill is to make mistakes and learn from them. Now that we understand how SQL works, we'll review how it looks. SQL is a generous language when it comes to formatting. New lines, capitalization, and indentation are not required in SQL as they sometimes are in other programming languages. For example, the code on this slide will run just fine, returning the first three titles, release years, and countries from the film's table. However, writing queries like this won't make us any friends in the SQL world because the lack of formatting makes the code difficult to read, especially as queries become more complex. Over time, SQL users have developed style standards that are generally accepted across industries. This code returns the same results as the code on the previous slide, but it is much easier to read due to the addition of capitalized keywords and new lines between them. While keyword capitalization and new lines are standard practice, many of the finer details of SQL style are not. For instance, some SQL users prefer to create a new line and indent each selected field when a query selects multiple fields, as the query on this slide does. Because of the different formatting styles, it's helpful to follow a SQL style guide, such as Hollywell's, which outlines a standard of best practices for indentation, capitalization, and naming conventions for tables, fields, and aliases. Remember, though, that there is no single required formatting in SQL. The guiding principle is writing clear and readable code. Have you noticed the sample code we've been looking at throughout this lesson has a semicolon at the end? Like capitalization and new lines, this semicolon is unnecessary in PostgreSQL. We could leave it out of the query and still expect the same results with no errors. However, including a semicolon at the end of the query is considered best practice for several reasons. First, some SQL flavors require it, so it's a good habit to have. Including a semicolon in a PostgreSQL query means that the query is more easily translated to another flavor if necessary. Additionally, like a period at the end of a sentence, a semicolon at the end of a query indicates its end, which is helpful in a file containing several queries. One last note on SQL style. While we can ensure our code is formatted beautifully, we don't have control over other people's SQL style. When creating a table, a SQL mistake is including spaces in a field name. To query that table, we'll need to enclose the field name in double quotes to indicate that, despite being two words, the name refers to just one field. For example, if a sloppy SQL coder had named a field release space year as two words, we'd need to update the query we've seen throughout this chapter to the one shown here. Adhering to SQL style guides allows for easier collaboration between peers. Having clean and readable code is highly valued in the community and a professional setting and will make things easier for anyone wanting to understand or debug our queries. Now that we've mastered selecting and counting data from a database, we'll add to our repertoire by learning about filtering. To filter, we need to use a new clause called where, which allows us to focus on only the data relevant to our business questions. Going back to our coat analogy, we may want to select a coat from the closet where the color is green. The where clause can help us with that. We will focus on filtering numbers in this lesson. To do this, we will be using comparison operators such as greater than. Here is an example of a query where we filtered to see only films released after the year 1960 using the greater than operator. Let's explore some of the other operators. We would use the less than operator to see films released before the year 1960. We would use the less than or equal to operator to see films released during or before the year 1960. If we want to see films released in a specific year, we can use equals. Here is a final example that isn't as intuitive as the others. If we wanted to filter films to see all releases except those from the year 1960, we would combine the less than and greater than symbols as shown here. This is the SQL standard symbol that means not equal to. Let's recap all the comparison operators we can use with where to filter numbers. We have greater than, that also means after, less than, that also means before, equal to, greater than or equal to, less than or equal to, and not equal to. Where in the comparison operator equals can also be used with strings. In these cases, we will have to use single quotation marks around the strings we want to filter. For example, here, we want to filter titles where the country is Japan. A final note on using where. Similar to limit, this clause comes after the from statement when writing a query. If we use both where and limit, the written order will be select, from, where, limit. However, the order of execution will now be from, where, select, limit. Thinking about the coats in our closet, we go to the closet we want to get the coat from, find where the green coats are, and select 5 of them. Great work on filtering numbers. Our SQL skills are growing fast. Next up, we will look at how to filter with multiple criteria. There will often be the case that we have more than one criteria we'd like to meet. Looking again at our favorite coats, perhaps we want to narrow down our choices to coats that are yellow and shorter in length. We will be learning about 3 additional keywords that will allow us to enhance our filters when using where by adding multiple criteria. These are or, and between. In the context of our coats, we could look at coats where the color is yellow or the length is short, or we could filter for coats where both criteria are true. We can also look for coats that have between 1 and 5 buttons. The first keyword we will look at is the or operator. Or is used when we want to filter multiple criteria and only need to satisfy at least one condition. Perhaps we want to select green or purple code options as an example. In SQL, we combine or with where to achieve this type of filtering. Here is an example using the films database. The query on the left returns all films released in either 1994 or 2000. Note that we must specify the field for every or condition, so the query on the right is invalid. That query hasn't specified what field or operator should be associated with the year 2000. If we want to satisfy all criteria in our filter, we need to use and with where. For example, this query gives us the titles of films released between 1994 and 2000. We need to specify the field names separately for every and condition as with or. Let's kick it up a notch. We now want to filter films released in 1994 or 1995, and with a certification of either PG or R. Thankfully, we can combine and or to answer this question. If a query has multiple filtering conditions, we will need to enclose the individual clauses in parentheses to ensure the correct execution order. Otherwise, we may not get the expected results. As we've learned, we can use this query to get titles of all films released in and between 1994 and 2000. Checking for ranges like this is very common. So in SQL, the between keyword provides a valuable shorthand for filtering values within a specified range. This second query is equivalent to the one on the left. It's important to remember that between is inclusive, meaning the results contain the beginning and end values. Like the where clause, the between clause can be used with multiple and or operators, so we can build up our queries and make them even more powerful. For example, we can get the titles of all films released between 1994 and 2000 from the United Kingdom. We're making excellent progress. We will now switch our focus away from filtering numbers to filtering textual data. As we've briefly seen, we can use the where clause to filter text data. However, So far, we've only been able to filter by specifying the exact text we're interested in. We'll often want to search for a pattern rather than a specific text string in the real world. We'll be introducing 3 more SQL keywords into our vocabulary to help us achieve this: like, not like, and in. In SQL, we can use the like operator with a where clause to search for a pattern in a field. We use a wildcard as a placeholder for some other values to accomplish this. There are 2 wildcards with like, the % and the underscore. The % wildcard will match 0, 1, or many characters in the text. For example, the query on the left matches people like Adele, Adelaide, and Aiden. The underscore wildcard will match a single character. For example, the query on the right matches only 3-letter names like Eve. We'd also see names like Eva if it were in our dataset. Eva Mendez, however, would not be visible unless the search criteria looked like this. We can also use the not like operator to find records that don't match the specified pattern. In this query, we are finding records for people who do not have a dot as part of their first name. It's important to note that this operation is case-sensitive, so we must be mindful of what we are querying. We've reviewed one example of where to position each wildcard, but we can actually put them anywhere and combine them. We can find values that start, end, or contain characters in any position, as well as find records of a certain length. For example, this code on the left will find all people whose name ends in R. The code on the right will find records where the third character is T. What if we want to filter based on many conditions or a range of numbers? We could chain several ORs to the where clause based on what we know, but that can get messy. We can see an example here where we select the film titles released in 1920, 1930, or 1940. A helpful operator here is in. The in operator allows us to specify multiple values in a where clause, making it easier and quicker to set numerous, or, conditions. So, the example shown on the previous slide would simply become where release underscore in 1920, 1930, 1940, where the years are enclosed in parentheses. Here is another example using a text field where we want to find the title where the associated country is either Germany or France. Our next lesson will review how to filter data that includes null values. When we were learning how to use the count keyword, we learned that we could include or exclude non-missing values depending on whether or not we use the asterisk in our query. But what is a missing or non-missing value? In SQL, null represents a missing or unknown value. Why is this useful? In the real world, our databases will likely have empty fields either because of human error or because the information is not available or is unknown. Knowing how to handle these fields is essential as they can affect any analyses we do. For example, we used count all with an asterisk on the left. Suppose our goal is to analyze posthumous success using data from the people table. We might make the wrong assumption that because we have a field name called death date, this information is available for everyone. Half of them are, in fact, null, as we can see on the right, so we would make an inaccurate judgment on what the data means. One quick way to see how much of our data is missing is by using is null with the where clause. Here is an example where we have checked to see which names do not have a recorded birth date in our table. On the left is an example of counting the missing birth dates in the people table. The count is 2,245. Sometimes, we'll want to filter out missing values, so we only get results that are not null. To do this, we can use the is not null operator. For example, this query on the right gives the count of all people whose birth dates are not missing in the people table, giving us a new count of 6,152. There may be a question about the difference between using count with a field name and using the same count with the added where clause with is not null. The answer is there is no difference, as both will be counting non-missing values. Before we wrap up this lesson, let's review what we've learned. Null values are missing values, and they are very common in the real world. It is good practice to know how many null values are in our data by using the isNull or isNotNull operator for filtering. These keywords will help to identify, select, or exclude missing values. Don't worry, this will soon become second nature because it is that common. Fantastic job getting this far. Let's learn about summarizing data with aggregate functions. When analyzing data, we often want to understand the dataset as a whole in addition to looking at individual records. One way to do this is to summarize the data using SQL's aggregate functions. An aggregate function performs a calculation on several values and returns a single value. We already know one aggregate function, count. We'll now learn 4 new aggregate functions, allowing us to find the average, sum, minimum, and maximum of a specified field. Let's look at some examples of how they work. These aggregate functions come after select, exactly like count. This first query gives us the average value from the budget field of the films table. That's an average of over 39 million per film in the films table. The sum function returns the result of adding the values in the budget field. Here, the total budget of all the films is over 181 billion. The min function returns the lowest budget, and the max function returns the highest budget. The 2006 South Korean movie, The Host, had a budget of over 12 billion. That sounds huge, but our data is in multiple currencies, so a true comparison would require currency exchange rates as well. Note that we operate on the field, or column, with all of these aggregate functions, not the records, or rows. Although these functions appear to be mathematical, we can use several of them with both numerical and non-numerical fields. Average and sum are the 2 aggregate functions we can only use on numerical fields since they require arithmetic. We can use count, minimum, and maximum with non-numerical fields as we already saw with count in previous lessons. Count can provide a total of any non-missing or not null records in a field regardless of their type. Similarly, minimum and maximum will give the record that is figuratively the lowest or highest. Lowest can mean the letter A when dealing with strings, or the earliest date when dealing with dates. And of course, with numbers, it is the highest or the lowest number. Here are some examples of using these functions with non-numerical fields. We can select the minimum and maximum country from the film's database and see that our minimum country, or country that would come first in the alphabet, is Afghanistan. In contrast, West Germany is the maximum country that would come last in the alphabet. Our database does not contain any films made in Zambia or Zimbabwe, but it does have at least one film made back when Germany was 2 different countries. Notice how all query results have automatically updated the field name to the function. In this case, min. It's best practice to use an alias when summarizing data so that our results are clear to anyone reading our code. Now we will combine our filtering skills with our new summarizing skills. We can combine aggregate functions with the where clause to gain further insights from our data. That's because the where clause executes before the select statement. For example, to get the average budget of movies made in 2010 or later, we would select the average of the budget field from the films table where the release year is greater than or equal to 2010. Here are a few more examples using the other functions. We find the total budget of movies made in 2010 using the sum function, that's over 8.9 billion. Next, we get the smallest budget using the min function, which is 65,000. Here, we query the highest budget using the max function. 600 million feels like a lot again for a movie budget, but this is in Indian rupees for the movie Kites. Finally, we query the count of the number of budgets using the count function, which gives us the total number of non-missing values in the budget field, meaning there are 194 budgets recorded for the year 2010 in the films table. Now that we are doing all sorts of things with our numerical values, we'll likely want to clean up some of the crazy decimals that might appear. In SQL, we can use round to round our number to a specified decimal. There are 2 parameters for round, the number we want to round, and the decimal place we want to round to. Here we have recalculated the same average budget as before, but this time we have included round and specified we want to round to 2 decimal places because we are dealing with currency. The second parameter in our round function is optional, so we can leave it out if we want to round to a whole number. We would get the same result if we passed 0 as the second argument, as it is the default when no number is given. Here's a tricky one. We could also pass a negative number as the second parameter and still get a result. Here, the function is rounding to the left of the decimal point instead of the right. Using -5 as the decimal place parameter will cause the function to round to the 100,000 or 5 places to the left. Round can only be used with numerical fields. In this lesson, we will learn about using more arithmetic in our queries and take a closer look at aliasing with as. We can perform basic arithmetic with symbols like plus, minus, multiply, and divide. Using parentheses with arithmetic indicates to the processor when the calculation needs to execute. Here are some basic examples of how we can use arithmetic in SQL. We can add, subtract, multiply, and divide as follows. In these examples, the parentheses are not required as only one calculation takes place. However, they provide more clarity to the code. But the division gives a result of 1. Why is that? Similar to other programming languages, SQL assumes that we want to get an integer back if we divide an integer by an integer. So be careful. When dividing, we can add decimal places to our numbers if we want more precision. For example, select 4.0 divided by 3.0 gives us the result we would expect, 1.3 repeating. What's the difference between using aggregate functions and arithmetic? The key difference is that aggregate functions, like sum, perform their operations on the fields vertically while arithmetic adds up the records horizontally. Before we move on, let's run through an arithmetic example using our database. Here we have selected the gross, how much the movie made, minus the budget, how much the movie cost, from our films table. The result is the amount of profit. Notice that the query's result doesn't give us a defined field name. We will always need to use an alias when summarizing data with aggregate functions and arithmetic. As we progress and learn how to manipulate our data, it will be even more important to keep our field names clear. For example, if we're using multiple max functions in one query, we'll have 2 fields named max, which isn't very useful. This is a situation when it's especially important to alias like we do here. Let's explore how using an alias fits into the SQL execution order. Here is a reminder of the order of execution we know so far. SQL will process the from statement first, followed by the where clause, then the select statement, and finally, limit. When adding an alias for a field name in the select clause, we might assume we could use it later in our query with the where clause. Unfortunately, that is not possible. As we can see by the order of execution, the query would not have created the alias yet, and our code would generate an error. Congratulations on making it this far. We'll now learn how to sort and group results to gain further insight. Sorting results means we want to put our data in a specific order. It's another way to make our data easier to understand by quickly seeing it in a sequence. Let's say we wanted to extract our 3 longest coats. If our closet were messy, it would take a long time to find. However, if we sorted our closet by garment type and length, we could quickly grab them. In SQL, the order by keyword is used to sort results of 1 or more fields. When used on its own, it is written after the from statement, as shown here. Order by will sort in ascending order by default. This can mean from smallest to biggest, or from A to Z. In this case, we have one query sorting the budget from smallest to biggest and a second query sorting the titles alphabetically. Our database contains film titles that start with symbols and numbers. These come before the letter A. We could also add the ASC keyword to our query to clarify that we are sorting in ascending order. The results are the same, and our code is more readable. We can use the desk keyword to sort the results in descending order. This query gives us the film titles sorted by budget from biggest to smallest. However, our data contains a lot of null values. We can add a where clause before order by to filter the budget field for only non-null values and improve our results. Notice that we don't have to select the field we are sorting on. For example, here's a query where we sort by release year and only look at the title. However, it is a good idea to include the field we are sorting on in the select statement for clarity. Order by can also be used to sort on multiple fields. It will sort by the first field specified, then sort by the next, etc. To specify multiple fields, we separate the field names with a comma. The second field we sort by can be thought of as a tiebreaker when the first field is not decisive in telling the order. Here is an example. Let's say we wanted to find the best movie. In the first query, we are only sorting the films by the number of Oscar wins and getting a tie. We can break that tie by adding a second sorting field by seeing which film has the most wins and the highest IMDb score. We can also select a different order for each field we are sorting. For example, here, we are sorting birth date in ascending order and name in descending order. Order by falls towards the end of the order of execution we already know, coming in just before limit. The from statement will execute first, then where, followed by select, order by, and finally, limit. We've learned how to sort data. Next, we'll look at grouping our results. In the real world, we'll often need to summarize data for a particular group of results. For example, we might want to see the film data grouped by certification and make calculations on those groups, such as the average duration for each certification. SQL allows us to group with the group by clause. Here it is used in a query where we have grouped by certification. Group by is commonly used with aggregate functions to provide summary statistics, particularly when only grouping a single field, certification, and selecting multiple fields, certification and title. This is because the aggregate function will reduce the non-grouped field to one record only, which will need to correspond to one group. SQL will return an error if we try to select a field that is not in our group by clause. We'll need to correct this by adding an aggregate function around title. We can use group by on multiple fields similar to order by. The order in which we write the fields affects how the data is grouped. The query here selects and groups certification and language while aggregating the title. The result shows that we have 5 films that have missing values for both certification and language, 2 films that are unrated and in Japanese, 2 films that are rated R and in Norwegian, and so on. We can combine group by with order by to group our results, make a calculation, and then order our results. For example, we can clean up one of our previous queries by sorting the results by the title count in descending order. Here is that query without order by, and this is the same query with ordering added. Order by is always written after group by, and notice that we can refer back to the alias within the query. That is because of the order of execution. It looks like movies rated are most common in our database. Group by fits into our order after from and before all other clauses. Our updated queries will begin with from, followed by grouping, selecting the data and creating the alias, sorting the results, and limiting them to the desired number. That was excellent work. We've combined sorting and grouping. Next, we will combine filtering with grouping. In SQL, we can't filter aggregate functions with where clauses. For example, this query attempting to filter the title count is invalid. That means that if we want to filter based on the result of an aggregate function, we need another way. Groups have their own special filtering word, having. For example, this query shows only those years in which more than 10 films were released. The reason why groups have their own keyword for filtering comes down to the order of execution. We've written a query using many of the keywords we have covered here. This is their written order, starting with select, from films, where the certification is G, PG, or PG, 13, group by certification, having the title count be greater than 500, order by title count, and limit to 3. In contrast, The order of execution is from, where, group by, having, select, order by, and limit. By reviewing this order, we can see where is executed before group by and before any aggregation occurs. This order is also why we cannot use the alias with having, but we can with order by. Where filters individual records while having filters grouped records. We'll walk through 2 business questions here to show how to translate them into the correct filter. The first question is, what films were released in the year 2000? This question does not indicate any sort of grouping. It asks to see only the titles from a specific year and can therefore be written as select title from films, where release year equals 2000. The second question is, in what years was the average film duration over 2 hours? Straight away, we can see this question has a few more layers. Let's break down the question and query into smaller, easier to understand steps. This question requires us to return information about years, so we select the release year from the films table. Next, it asks for the average film duration, which tells us we need to place average duration somewhere. Since we do not need to provide any additional information around the duration on its own, it is unlikely we need to perform the aggregation within the select clause, so we'll try the having clause instead. The last part of the question indicates we need to filter on the duration. Since we can't filter aggregates with where, this supports our theory about using having. Finally, we need to add a group by into our query since we have selected a column that has not been aggregated. Recall the aggregate function will convert the duration values into one average value. Going back to the start of our question, we're interested in knowing the average duration per year, so we group it by release year. And there we have it.